On the 23rd of July, 1983, a brand new Boeing 767 Jetliner was cruising at 41,000 feet over central Canada with 61 passengers and 8 crew aboard when first one engine, and then the other, went silent. The aircraft had not suffered a mechanical failure. The engines were in perfect condition. They had simply completely run out of fuel. At 41,000 feet, in an airplane that was now, for all practical purposes, a 130-ton glider. And here's the part that has made this story legendary among pilots and engineers ever since. The airplane did not run out of fuel because of a leak. It did not run out because a gauge failed or a pump broke. It ran out of fuel because on the ground before takeoff, somebody did a calculation, a simple multiplication to work out how much fuel to load, and used the wrong number. One number, in one conversion, was off, and because of it, the airplane left the ground carrying roughly half the fuel everyone believed it had. What followed was one of the most extraordinary feats of flying in the history of aviation. This is the story of the jetliner that ran out of sky. To understand how a jetliner ran out of fuel in midair, you have to understand two changes that were happening at the same time in 1983, and that happened to collide. The first change was the airplane itself. The Boeing 767 was, in 1983, a brand new aircraft type. Air Canada had only just begun flying them, and the 767 was modern in a way that mattered enormously for this story. Older airliners had a flight crew of 3 pilots and a flight engineer, a third crew member whose job was to manage the aircraft's systems, including its fuel. The 767 was designed for a crew of 2. The flight engineer's role was gone, absorbed into automated systems and into the duties of the 2 pilots. The aircraft also had advanced electronic instruments and a computerized fuel system that, when working properly, automatically measured the fuel on board and tracked how much remained. It was a sophisticated modern machine, and both pilots and ground crews were still, in 1983, relatively new to it. The second change happening in Canada in 1983 was bigger than any one airplane. The country was in the middle of converting to the metric system. For most of its history, Canada, like the United States, had used imperial units, pounds, feet, gallons. But through the 1970 seconds and into the 1980 seconds, Canada was officially switching to the metric system: kilograms, meters, liters, and this conversion reached into aviation. Older aircraft in the Air Canada fleet measured their fuel in pounds. The new Boeing 767 was, notably, the first aircraft in the Air Canada fleet designed to be operated using metric units. Its fuel was to be measured in kilograms. Now pause on that, because it is the seed of everything that follows. You have a brand new type of airplane, with a brand new 2-person crew concept being introduced into a fleet, in a country, in the middle of a transition between 2 entire systems of measurement. The old airplanes thought in pounds. This new airplane thought in kilograms. And the people on the ground, the pilots, the mechanics, the refuelers, were working across both worlds at once. When a system is changing, the most dangerous place to stand is with 1 foot in the old world and 1 foot in the new. And in July 1983, that is exactly where everyone around this airplane was standing. Now I need to give you the single most important technical idea in this whole episode, and it is something most people never think about. When you put fuel into an aircraft, the quantity that actually matters, the quantity the pilots and the flight plan truly care about, is not volume, it is mass. Let me explain why, because it is genuinely interesting. A flight plan is, at heart, an energy calculation. The aircraft needs to do a certain amount of work to fly a certain distance, to overcome drag to stay aloft, and that work is done by burning fuel. The amount of energy in a load of jet fuel depends on its mass. So many kilograms of fuel contain so much energy and will take you so far. So pilots plan in mass. They calculate that the flight requires a certain number of kilograms, or in the old system, a certain number of pounds of fuel. But here is the problem. You do not pump mass into an airplane. A fuel truck does not deliver kilograms. A fuel truck delivers volume. It pumps a certain number of liters, or a certain number of gallons, of liquid into the tanks. So at the airport on the ground, there is always a conversion that has to happen. The flight plan says, I need this many kilograms of fuel. The fuel truck speaks in liters. Somebody has to convert between them. And to convert a volume of fuel into a mass of fuel, you need one specific number. You need to know the density of the fuel. So let us talk about density, because density is the quiet hinge that this entire story turns on. Density is a simple idea. It is how much mass is packed into a given volume of a substance. Water, for example, has a density of about 1 kilogram per liter. 1 liter of water has a mass of about 1 kilogram. Jet fuel is lighter than water. It floats on water, so a liter of jet fuel has a mass somewhat less than a kilogram. To convert a volume of jet fuel into a mass of jet fuel, you multiply the volume by the density. Liters times density gives you mass. It is a single multiplication. And the whole catastrophe of Air Canada Flight 143 lives inside that single multiplication, because the density of jet fuel can be written in different units, and the number is completely different depending on which units you use. If you express the density of that jet fuel in metric units, in kilograms per liter, it is a number a bit less than 1, in this case around 0.8, roughly 0.8 kilograms in every liter. But you can also express the density of the very same fuel in imperial units, in pounds per liter. And in pounds per liter, the density of that fuel is a number around 1.7. Same fuel, same liquid in the same tank. Two completely different density numbers, around 0.8 or around 1.7, depending entirely on whether you are thinking in kilograms or in pounds. Do you see the trap now? It is not subtle once you see it, and that is exactly what makes it so frightening. If you want to load a certain mass of fuel in kilograms, and you know the volume in the tanks in liters, you must multiply the liters by the density in kilograms per liter, by the number around 0.8. If you accidentally multiply by the imperial density instead, by the number around 1.7, you will get an answer that is roughly twice as large as it should be, because 1.7 is roughly twice 0.8. The wrong density is about double the right one. So the error has a specific terrible magnitude built into it. It is not a small error, it is almost exactly a factor of 2. Use the imperial density number when you needed the metric one, and your calculation of the fuel will be off by roughly double. And that is the heart of what happened on the ground in 1983. Somewhere in the chain of people working out how much fuel to put into that Boeing 767, the imperial density figure, around 1.7, was used in a calculation that needed the metric figure, around 0.8. The number was wrong by a factor of 2, and so the airplane's fuel load was wrong by a factor of 2. Now, you might reasonably ask, why was anyone doing this multiplication by hand at all? The Boeing 767 had a computerized fuel system designed to measure and track the fuel automatically. The crew should not have needed to manually convert anything. And that is true on a normal day, but the 23rd of July, 1983 was not a normal day for this particular aircraft. The 767's automatic fuel measurement depended on a piece of equipment called the fuel quantity processor. And on this aircraft, that system was not working correctly. There had been a problem with the fuel quantity indication. So the automatic system that should have simply told the crew how much fuel was on board could not be relied upon, which meant the fuel quantity had to be determined another way, by a manual procedure on the ground, using a measuring device called a dripstick, or drip gauge, to physically measure the level of fuel in the tanks, and then converting that measurement into a quantity of fuel. A manual measurement of volume, followed by a manual conversion into mass, followed by the multiplication. The exact multiplication that needed the density. The broken automatic system is what forced the calculation out of the computer and into human hands. And human hands, that day, working across two systems of units, reached for the wrong number. So let us walk through what actually happened on the ground at Montreal and then at Ottawa before Flight 143 took off, because the error was not a single careless moment, it was a calculation done carefully with the wrong ingredient. The crew and ground personnel needed to determine how much fuel was already in the tanks and how much more to add so that the aircraft would depart with the fuel load the flight plan required. The flight plan for this metric aircraft specified the required fuel as a mass in kilograms. Using the dripsticks, the fuel already in the tanks was measured as a volume, in liters. Now the conversion had to be done. The volume in liters had to be turned into a mass, so it could be compared against the kilograms the flight plan called for. And in performing that conversion, the figure used for the density of the fuel was the imperial figure, the pounds per liter number, around 1.7, rather than the metric figure, the kilograms per liter number, around 0.8. The multiplication itself was done correctly. Liters times density, the arithmetic was not the problem. The problem was that the density that went into the correct arithmetic was the wrong density. And so the mass of fuel that came out was wrong. Here is the precise, cruel shape of the mistake. Because the imperial density, around 1.7, is roughly twice the metric density, around 0.8, the calculation produced a figure for the existing fuel that expressed as a mass was far too large. The volume of fuel actually in the tanks contained a certain mass in kilograms, but multiplied by the wrong roughly doubled density figure. The calculation reported that the tanks already held far more mass of fuel than they truly did. So when the crew compared this inflated figure against the kilograms the flight plan required, the conclusion was that the aircraft only needed a relatively small amount of additional fuel to reach the planned total. The additional fuel was loaded based on that conclusion, and so the Boeing 767 pushed back from the gate, believing it carried the full fuel, load the flight to its destination required. When in reality, because the existing fuel had been so badly overcounted, the tanks held only around half of the fuel mass that everyone believed was on board. The flight plan said the airplane had enough fuel to fly to its destination with a comfortable reserve. The airplane actually had enough fuel to fly roughly halfway there. Now, there is something important to say here, and it is the reason this story is taught the way it is. It would be easy and lazy to tell this as the story of one careless person who reached for the wrong number. That is not what the investigation found, and it is not the honest version. The Canadian investigation into Flight 143 found a chain of contributing factors. An accident that, like most serious accidents, was not caused by a single villain, but by a system in which several layers of protection all happened to be weak at the same time. The aircraft was operating with a known fault in its fuel quantity system, which forced reliance on the manual procedure. The airline was in the middle of a difficult, incomplete transition to metric units, and procedures and training around that transition were not yet fully solid. The manual fuel measurement and conversion procedure itself was not robust enough to reliably catch a unit error, and the people involved, pilots, maintenance staff, ground crew, were all working in good faith inside that imperfect system, across two systems of units with a new aircraft type. The wrong density number was the immediate trigger. But the reason the wrong number was not caught, the reason it survived all the way to the tanks and into the air, is that every layer that might have caught it was, that day, too thin. That is the real anatomy of the error, not one mistake that nothing else stopped. So now we reach the question at the heart of this story. How does a single wrong number used on the ground turn into two silent engines at 41,000 feet? To see it clearly, we have to follow the consequences of that error forward step by step into the flight itself. The airplane took off. It departed with what everyone believed was a full fuel load, and was in reality roughly half of one. Now, here's the first thing to understand. An aircraft burns fuel continuously, and at a rate. The engines consume a certain mass of fuel every hour to produce the thrust that keeps the airplane flying. The flight plan is built on this. It says, in effect, the aircraft will burn fuel at roughly this rate. The flight will take roughly this long. Therefore, the flight will consume roughly this much fuel, and so we must load that much, plus a reserve. The fuel burn calculation in the flight plan was, in itself, correct. The engines would indeed burn fuel at the expected rate. The flight would indeed take the expected time. The flight plan correctly calculated how much fuel the journey would consume. The only thing wrong was the belief about how much fuel had actually been loaded to meet that consumption. So picture the flight unfolding. The airplane is cruising. The engines are burning fuel at the normal expected rate. The fuel is draining from the tanks, draining at the rate the flight plan predicted. But it is draining out of a quantity that was only half of what it should have been. So the fuel was always going to run out roughly halfway through the planned journey. Not because anything was burning fuel too fast, the burn rate was normal, but because the supply being burned was half the assumed size. Think of it as a simple, brutal piece of division. The distance you can fly is roughly the fuel you have divided by the rate you burn it. The burn rate was right, but the fuel you have was halved. Halve the top of that fraction, and you have the answer. Have the fuel, and you have the range. An airplane that everyone believed could comfortably reach its destination could, in physical reality, fly only about half that far. And the crew, looking at instruments and paperwork that all traced back to the same wrong number, had no reason, at first, to know it. Now, here is where the story turns from a quiet error into a genuine emergency, and it happened in stages. As Flight 143 cruised over Canada, the fuel in the tanks was running down toward a level no one expected it to reach, and then the warnings began. The aircraft's systems gave the crew indications of a fuel problem. At first, the situation was confusing. The crew was getting alerts they had not anticipated on a new aircraft type, with a fuel measurement system already known to be unreliable. The flight crew, Captain Robert Pearson and First Officer Maurice Quintal, recognized they had a fuel emergency developing and began to divert, turning toward Winnipeg to land. But the fuel was going faster than even the emergency picture suggested. because the true quantity had been so low to begin with. And then while the aircraft was still well over 100 kilometers from Winnipeg, and at cruising altitude, the left engine ran dry, lost power, and went silent. The crew now had one engine, and a true emergency, and a hard descent ahead. And then, only minutes later, the right engine, the last engine, also ran out of fuel, and it stopped at 41,000 feet over central Canada. The Boeing 767 had become a glider. I want you to sit for a moment with what the loss of both engines actually means on a modern jetliner, because it is worse than just losing thrust. On an aircraft like the 767, the engines do not only provide forward push, they also drive the generators that produce the aircraft's electrical power, and they drive the systems that provide hydraulic pressure for the flight controls. When both engines stopped, most of the cockpit's electronic instrument displays went dark. The crew lost the bulk of their modern instrumentation. But the aircraft had a last resort backup, and it is a wonderful piece of engineering. It is called a ram air turbine, a small turbine like a little windmill that drops out into the airflow when normal power is lost. As the airplane glides through the air, the rushing wind spins that little turbine, and it generates just enough hydraulic and electrical power to keep the most essential flight controls and a minimal set of instruments alive. The airplane itself, by drawing power from its own forward motion through the air, kept just enough capability for the pilots to fly it. But that was all they had. A minimal aircraft, no engines. A few essential instruments, powered by a windmill, 69 souls aboard, and a long, silent, descending glide. So let us actually write down the equation, or rather, the chain of simple equations, that emptied the tanks of Air Canada Flight 143. It begins with the conversion. The mass of fuel equals the volume of fuel multiplied by the density of the fuel. Mass equals volume times density. That is the entire equation at the root of this disaster, and it is the kind of equation a school child can handle. There is nothing difficult about it. There is no advanced mathematics anywhere in this story. The 767 did not fall out of the sky because of a hard equation. It fell out of the sky because of an easy one, fed a wrong ingredient. The error was entirely in the density term. The equation called for the density expressed in kilograms per liter. The value supplied was the density expressed in pounds per liter, a number roughly twice as large. And because the equation is a simple multiplication, an error of a factor of 2 in one input produces an error of a factor of 2 in the output. The math faithfully, obediently, carried the wrong density straight through to a wrong mass. Now here is the idea I most want you to take from this episode, and it is a genuinely deep one. A number by itself is meaningless. A number only has meaning when it is attached to a unit. The figure 1.7 is not a density. The figure 0.8 is not a density. A density is 1.7 pounds per liter, or 0.8 kilograms per liter. The unit is not decoration. The unit is half of the quantity. When you strip the unit off a number and treat the bare figure as if it were the whole thing, you have thrown away the information that tells you what the number actually means. And you have created the conditions for exactly this kind of catastrophe. The equation mass equals volume times density is only true if every term is in a consistent system of units. Liters and kilograms per liter give you kilograms. Liters and pounds per liter give you pounds. Mix them, feed pounds per liter into a calculation whose answer you will read as kilograms. And the equation does not protest. It does not stop. It cannot. An equation has no way of knowing what units you intended. It simply takes the numbers you give it and returns a number. The meaning, the units, live entirely in the mind of the person using it. And on the 23rd of July, 1983, the units in the equation and the units in the human mind reading its answer did not match. So let us assemble the full chain, the complete equation of the accident, in order. First, the existing fuel was measured as a volume in liters. That measurement was correct. Second, that volume was converted to a mass using mass equals volume times density, but the density used was the imperial figure, around 1.7, instead of the metric figure, around 0.8, so the mass that came out was roughly double the true mass. Third, the additional fuel to be loaded was calculated by subtracting that inflated existing mass figure from the total mass the flight plan required. Because the existing fuel had been overcounted, the additional fuel was undercounted. Fourth, the airplane took off carrying roughly half the fuel mass that everyone believed was aboard. Fifth, the engines burned that fuel at the normal, correctly predicted rate. And so, with range equal to fuel divided by burn rate, and the fuel halved, the airplane's true range was roughly half the planned distance. Sixth, roughly halfway to the destination, the tanks ran dry, and the engine stopped. Every single step in that chain except one was performed correctly. The measurement was right. The arithmetic was right. The burn rate was right. The flight plan was right. One term in one multiplication carried the wrong unit, and a single wrong unit, propagated faithfully through a chain of correct calculations, was enough to silence a jetliner at 41,000 feet. So let us go back to the aircraft with the equation in hand and both engines silent at 41,000 feet. The crew now faced a problem that no airline pilot is ever truly expected to face. They had to land a large jetliner with no engines. And the first thing they needed was a number of their own, a good number this time. They needed to know how far the airplane could glide. An aircraft without engines is not falling helplessly. It is gliding. It trades altitude for distance. As it descends, it moves forward. The ratio of how far it travels forward to how far it descends is called the glide ratio. And for a clean jetliner, that ratio is surprisingly good. A 767 with no engines glides forward roughly 12 times as far as it descends. First Officer Maurice Quintal began calculating. Using their altitude and their distance from Winnipeg, he worked out whether the aircraft could actually glide all the way to the airport they were diverting to. And the answer he reached was no. The airplane was descending too fast, relative to its distance from Winnipeg. They were not going to make it to Winnipeg. They were going to come down short somewhere in between with no engines, in a 130-ton aircraft. And here is where an extraordinary, almost unbelievable piece of personal history enters the story. First Officer Maurice Quintal had earlier in his life been a pilot in the Royal Canadian Air Force, and he had personal knowledge of a former Air Force base, a place called Gimli, on the shore of Lake Winnipeg. Quintal knew that Gimli had a long runway, a former military airstrip. It was much closer than Winnipeg. It was in fact within gliding range. So the crew made the decision. They would not try for Winnipeg. They would glide the powerless 767 to the old airfield at Gimli. But what neither pilot fully knew was that the former Air Force base at Gimli was no longer a quiet, disused airfield. Part of the old airbase had been converted. One of its runways was now used as a racetrack and recreational facility. And on that very day, on that very strip of former runway, there was an event taking place. There were people and vehicles and families on the ground at Gimli. The crew was gliding a silent jetliner toward a runway that was, that afternoon, in active use by the public. The glide to Gimli was a feat of pure flying skill. Captain Robert Pearson brought to it an unusual asset. He was an experienced glider pilot. He had flown engineless aircraft for sport, and he understood, in his hands and his instincts, how to manage the energy of an aircraft that has no engines. And he needed every bit of it because as the 767 approached Gimli, a new problem appeared. The airplane was too high and too fast. It had energy to spare, which, for a glider on its one and only approach, with no chance to go around, is dangerous in its own way. Come in too hot, and you overshoot the runway entirely. To lose that excess height and speed, Pearson performed a maneuver called a forward slip, a technique well known to glider pilots. The aircraft is deliberately flown slightly sideways to the direction of travel, crossing the controls, which dramatically increases drag and lets the airplane descend steeply and shed energy without gaining speed. To do a forward slip in a large airliner, on final approach with no engines, with people on the runway ahead, that is flying of a kind that simply is not in the manual. Pearson slipped the 767 down toward the old runway at Gimli. The landing gear had been lowered, though the nose gear did not lock fully down, and the silent, gliding jetliner came down out of the sky toward a runway full of people. What happened in the final seconds at Gimli was against every reasonable expectation, survivable. The Boeing 767 touched down hard on the old runway. The main landing gear held. The nose gear, which had not locked fully down, collapsed, and the nose of the aircraft dropped and scraped along the runway surface. And that scraping nose, dragging on the pavement, actually helped. It added friction. It helped slow the aircraft down, on a runway shorter than a 767 would normally use and with no engine reverse thrust available to brake. There were people on that runway. There were, by various accounts, individuals and vehicles connected to the racing event on the strip. The aircraft, hurtling down the runway with its nose dragging, came toward them. And the airplane stopped. It came to rest on the old runway at Gimli, nose down, before reaching the people ahead of it. A small fire started in the nose area, and it was put out. The passengers and crew evacuated the aircraft using the emergency slides. And because the nose of the aircraft was pitched down onto the ground, the rear of the aircraft was raised unusually high, making the rear slides very steep. and some minor injuries occurred during the evacuation itself. But that was the extent of it. All 61 passengers and all 8 crew members survived. The injuries were minor. Nobody on the ground at Gimli was killed. A jetliner had run completely out of fuel at 41,000 feet, glided to a former military runway, and landed. And everyone walked away. The aircraft itself, the Boeing 767 that became known immediately and forever as the Gimli glider, has its own remarkable postscript. The damage from the landing was, in the scheme of things, relatively limited. The aircraft was repaired, and then it went back into service. The Gimli glider flew on as a working aircraft in the Air Canada fleet for years. In fact, for decades. It was not finally retired until 2008, 25 years after that afternoon over Manitoba. An airplane that had run out of fuel in mid-air and made a powerless emergency landing went on to fly passengers safely for a quarter of a century afterward. But the deeper legacy of Flight 143 is not the airplane. It is the investigation, and what was changed because of it. The Canadian Board of Inquiry into the accident examined the whole chain: the faulty fuel quantity system, the metric transition, the inadequate procedures, the way the unit error had been able to propagate uncaught. And the result was a set of changes to procedures, to how fuel quantity is determined and cross-checked, to how unit conversions are handled, to the safeguards around fueling an aircraft, designed so that a single wrong density figure could never again travel unchallenged, all the way from a clipboard on the ground to 2 silent engines in the sky. And there is a question worth asking, honestly, about the crew. Robert Pearson and Maurice Quintal did something genuinely extraordinary that day. They took an aircraft that had become a glider at high altitude, and they brought it down without the loss of a single life. Their conduct in the emergency, Pearson's gliding skill, Quintal's knowledge of Gimli, the forward slip, the whole improvised, disciplined recovery, is studied and admired in aviation to this day. But it is important to hold 2 things at once. The crew flew the emergency brilliantly, and the emergency should never have existed. The fuel error was a systemic failure that the crew were part of. The chain of contributing factors reached into the cockpit as well as the ground. The same investigation that praised the airmanship also laid out soberly how the airplane came to be in the air with half its fuel. And that is the honest shape of the Gimli glider story. It is, at the same time, a story of a system that failed and let a wrong number fly, and a story of human skill that reached into that failure and pulled 69 people back from it. Both halves are true. The error was real. The flying was magnificent. And the lesson lives in the space between them. The Gimli glider is now, in aviation and engineering education worldwide, one of the most widely told case studies that exists. It is taught in aviation safety as a textbook case of how an aircraft can be dispatched with a fuel load that is catastrophically wrong, and of the layers of cross-checking that must exist to prevent it. It is taught in the study of human factors as a model of an accident with no single villain. An accident that emerged from a faulty system, an incomplete transition, and thin procedures all aligning at once. And it is taught again and again in engineering and science courses everywhere as the most vivid possible warning about units, about what happens when a number is separated from the unit that gives it meaning. All of those readings are true. But here is the thing about the Gimli glider that I find most haunting, and it is the thing that connects it to every other story on this channel, and also makes it, in one specific way, the most unsettling story of all. On this channel, the usual pattern is a missing equation. The mathematics that would have explained the disaster did not yet exist, or lived in another field, or was known but ignored. The Vasa-Tacoma Narrows, Chernobyl, each was, in its own way, a story of an equation that the world had not yet brought to bear. But the Gimli glider is not that. The equation was not missing. The equation was mass equals volume times density. It is one of the simplest equations in all of physics. Every person in this story knew it. A child knows it. The equation was not missing, and it was not difficult, and it was not in another field. It was right there, fully known, completely standard, and it was even used. The disaster did not come from not having the equation. It came from feeding the equation a number whose unit was wrong, and from a chain of systems too thin to catch it. Every other disaster on this channel is a story about the limits of human knowledge. The Gimli glider is a story about something humbler, and, in a way, scarier. It is a story about how the simplest known equation in the world will still, obediently, and without complaint, fly an airliner's tanks dry if you hand it the wrong unit, and nothing stops you. I want to leave you with the thought I find most important about the Gimli glider, and it is the reason this story belongs on this channel. We have a deep and comforting belief that mathematics is a kind of safety. That if the equation is right and the arithmetic is right, then we are protected. The Gimli glider is the proof that this belief by itself is not enough. The equation was right, the arithmetic was right, and the airplane still ran out of fuel at 41,000 feet. Because an equation does not understand the world. An equation is a machine for turning numbers into numbers. It does not know whether a figure means kilograms or pounds. It does not know whether your answer will keep an airplane in the sky or drop it out of one. All of that meaning, the units, the intention, the connection between the symbols and the real physical liquid in a real physical tank. All of that lives in the human being using the equation. The equation holds up its end perfectly. It is the meaning that has to be guarded, and meaning is fragile. It is carried on a unit label, a word, a shared understanding between a clipboard and a calculator and a mind, and any of those can slip. The deepest lesson of the Gimli glider is that the equations governing the world are perfectly faithful and perfectly blind. They will carry whatever you give them all the way to the end, with total obedience, the right number, or the wrong one, exactly the same. The arithmetic is never the weak point. The weak point is always the moment a human being attaches a meaning to a number. Guard that moment, or the equation will very faithfully fly you out of the sky. Air Canada Flight 143 ended on an old runway at Gimli with 69 people alive, an aircraft that would fly for another 25 years, and a lesson that reshaped how the world fuels its airplanes. The procedures were rewritten, the cross-checks were strengthened, the metric transition in time was completed, and the wrong density number that emptied those tanks became one of the most carefully guarded against errors in aviation. The Jetliner ran out of sky because a number lost its unit, and it landed safely because two pilots reached into that failure with extraordinary skill. Strange equations are not always strangers, and they are not always difficult. Sometimes the equation is the most familiar one you know, mass equals volume times density. And the danger is not in the equation at all, but in the silent, fragile, human act of deciding what its numbers mean. The equation will always run, it will always be faithful, it only ever asks one thing of us in return, that we hand it the truth at Gimli. For one afternoon we did not. And the sky, very obediently, ran out. If you enjoyed this one, the story of a spacecraft sent to Mars that was lost for almost exactly the same reason, a quiet mismatch of units, this time between two teams of engineers that sent the Mars Climate Orbiter to its destruction, is a story for another day. Strange Equations is here for the math behind the moments that nobody at the time was calculating. If that is your kind of channel, subscribe. Thank you for watching.